Okay, so I think now is good time to start. First of all, thank you, all of you, for attending this third webinar of B2Space. My name is Valentin Canales. I'm one of the co-founders and director of B2Space. Well, with our other partners, we created the company back in 2016 with one dream in mind, which is to launch satellite to orbit, and doing that in an unconventional way. But you will be seeing shortly about that. So I'm going to start sharing a presentation, and I hope that you enjoy it. Good. Can you see my presentation? Good, perfect. So as I was mentioning, B2Space is a company that was created in the UK, but now we have as well subsidiaries in Spain, and we are developing innovative solutions. Our main goal as well is to develop a system to launch satellites into low Earth orbit. It is called the Raccoon system. You may think, what is a raccoon? What does it mean? Basically, well, we were inspired by a video from Red Bull Stratos. If you remember this crazy Austrian guy, Felix Baumannter, that jumped from a stratospheric balloon at 36 kilometers of altitude. So we said, what if we put a rocket beneath the balloon at that altitude? So what started as a crazy idea then became as well a reality. We started doing the maths, the numbers, and as well we saw that was a feasible way to launch satellite into orbit, where we could save a lot of fuel. So as the atmosphere and the stratosphere is up to 1,000 times thinner than on the ground level, we could save up to 80% of fuel, and therefore as well around 80% of cost compared to traditional launchers. So we started this route, and as we were developing this technology, as well, we saw synergies creating with our work, and started to develop another business lines as well that could as well benefit from the work that we have been creating. So these are the near space testing, which is what we are going to be talking about today. HAPS, high altitude pseudo satellites using our stratospheric balloons, but then as well consulting, where we have been, for example, supporting other companies such as Spaceport Cornwall and Virgin Orbit, preparing their safety cases. So who is B2Space? As I mentioned, we created the company in 2016, and we have a mix of teams as well as supporters that come from industry leaders. So at the moment, we are 18 engineers in the company that come as well from top aerospace companies. So the founders team, we met working for Airbus here in Bristol in the UK, but our team members come from companies such as Rolls-Royce, GE Aviation, and Embraer, among others. But as you can imagine, we are not doing this alone. We basically are making use of strong partners that are helping us. So this is from the European Space Agency, their incubation center in Harwell, Thales Alenia Space, Snowdon Aerospace Center, and other companies. With the help of this and our strong team, we are developing technologies that we think will disrupt the space industry. Now, getting more into near space testing. So what is near space testing? So to describe that, first, we are going to talk about the stratosphere and why the stratosphere is interesting as well to perform tests. So the stratosphere is the layer of the atmosphere that you can read that is above the troposphere and extends from 10 kilometers up to 50 kilometers of altitude from the Earth's surface. As I mentioned before, at this altitude, the atmosphere is 1,000 times thinner than on the ground. So this, jointly with other characteristics such as the high radiation levels that we can encounter in this area, makes it a perfect laboratory with conditions that are similar to the ones that can be found in low Earth orbit. Obviously, they are not the same as in low Earth orbit, but can provide significant opportunities. So for example, at 50 kilometers of altitude, as the atmosphere is so thin, there is almost negligible convection activities. So the heat exchange is mainly due to radiation, which is what happens in orbit. So for example, if you want to test how well your batteries or other systems are radiating heat to the exterior, you can use this. This can be a complement or even as well in some occasions replace some traditional testing such as baking thermal chambers as well on the ground. So how we came about this? So as well with the support of the European Space Agency Incubation Center in Harwell, UK, we developed this new service, what we call Near Space Testing Service, which in the end is a flying lab. So we are using our stratospheric balloon to basically fly this lab to the stratosphere to have altitudes that will range from 18 kilometers to up to 40 kilometers. and be able to perform different operations. So basically, we set this service in mind for basically small satellite manufacturers or subsystems manufacturers or different R&D or research projects that wanted to test, qualify, validate, or perform proof of concepts of their project in a way where they can not only, let's say, test their functionalities, but as well replicate real-life missions. And why? Because what we have mentioned, the stratosphere has extreme conditions that are similar to the ones that are presented in orbit. So as I mentioned, near baking conditions, we have big temperature gradients and as well very high radiation levels. In summary, what this offers as well, it is a speed up on the development cycles because companies, universities, researchers can speed up their development cycles and as well reduce cost compared to what you have to as well spend on basically booking and using the very expensive thermal vacuum chambers. So as well, a little bit more about the near space testing service. So as well as I mentioned, the cruise altitudes for these stratospheric balloon flights are from 18 to 14 kilometers. At the moment, the length of our missions is from 2 to 24 hours, and we are increasing as well that to up to 14 days from, oh, this is a small mistake, it should be next year, where as well we will have additional launch locations to have these extended flight opportunities. So we take care of everything. So we can pick up your payload, prepare it for flight, and then return it. At the moment, we are prepared to lift payloads of up to 100 kilos and supply the payloads with electrical power, telemetry, and as well an images pack on demand as well. So this is very, very nice as well, because as you can see later on some pictures, having payload figure against the black sky or the, let's say, the black space, it is something as well very powerful, let's say, as well in terms of marketing material, I have to say. So we have standard missions where we are flying our balloons regularly, but then as well we can support you preparing bespoke missions. If you want to perform, for example, drop test of parachutes because you want to test hypersonic parachutes, supersonic parachutes, or you want to, I don't know, perhaps a microgravity testing for any kind of application that you can have, we can help you as well prepare the right testing for that. It can be used as well to characterize materials, how they perform, for example, for a long time in the stratosphere with high UV radiation levels. Is your material going to resist and the long term as well? Is going to degrade quickly? And as well, we can perform as well mission simulations. If you are, I don't know, a company that wants to provide IoT solutions for the agricultural world, like, for example, sensors that are based on the soil to provide information through satellites, then we can simulate or prove your technology. We will fly our balloons with your reception system or your satellite system and test the concept, how it's going to be communicating and sending information back and forth. So you can prove to your customers, to your investors, how it works before you send anything to orbit, therefore saving you a lot of money. Then as well, we have designed this with basically one thing in mind, which is ease of integration of the payloads. So we have standard interfaces that make us as well being able to onboard different kind of payloads in a quick way. So there are not a lot of, let's say, preparation time, and we can fly almost straight away. So we can as well perform regular flights with right share opportunities. That means that your payload can travel with other payloads in order to provide cost savings. But as well as I mentioned, we can prepare specific missions just for you. So you are able as well to define how high you want to fly, how long, in which area, and what are the test objectives. But this right share opportunity is something very interesting as well, mainly in the first stages of your development, where you can start testing and validating your technology without having to spend a lot of money on it. So about launch locations. So currently we have 2 launch locations in the UK and 1 in Spain. So in the UK at the moment, our main center of launch is Spaceport Snowdonia and Snowdonia Aerospace Centre, which is in the northwest of Wales, where we are able to perform different kind of missions. Then as well, we have another launch site in Spain, in León, in Castilla y León region, where as well we are able to perform other kind of testings. In the future as well, we are going to open different spaceports worldwide. Why? The main reason is that obviously, as you can imagine, balloons are quite dependent on weather. So for example, if we don't have good weather in Spain, we could take the balloon to the UK. Or if we want to perform a mission for a long time and not going into the sea, potentially we will go to Australia, where we are already talking, for example, with the Northern Territory, Alice Springs, where it's as well a nice location as well to launch stratospheric balloons and have it flying for days without basically going to anywhere populated or before going into the sea. So as well as we grow, we intend to open launch locations worldwide, and then as well we will have capabilities as well and capacity to launch from the sea. This will allow us as well to find where is the launch, let's say the right location in terms of weather or potential trajectory or area of interest that we want to fly. So our system is very compact, so it could be shipped anywhere in the world quite quickly. So basically everything is fit into a container, shipped, and then our teams locally will be able to perform the mission or come as well with the components and perform the flight on your location. And as well, a schematic basically about our test bench, how it looks, let's say. So as I mentioned, it is specifically designed to fit CubeSats, and it can fit it in different positions. So currently let's say we have more demand for, let's say, 1U CubeSats and 3U CubeSats, and those can be placed in different directions. So for example, they can be placed vertically, different sides, for example, or they can be placed horizontally. So at the moment, we can host up to 4 payloads in each flight, and potentially as well increasing it into the future. Or for example, if one customer wants to fly its own, let's say 12U CubeSat, it could book the whole flight for them. As well, just to let you know that this is a modular structure. So in case that a customer wanted to fly a really big payload, for example, when we are talking about 100 kilos payload, this structure can be grown as well to be able to host larger payloads. As I mentioned, at the moment, it is very easy to integrate the payload because we have standard connections, but as well, we can perform custom designs and adaptations. Some examples here as well, the kind of standard fittings that we have. So we have designed our system with, say, as well to be able to fit rail type CubeSats, where, as you see, for example, here we have rails as well that can be loaded and fitted, or as well that are called, let's say, tap type CubeSats. So depending on which kind of CubeSat do you have or component do you have, we will be able to easily fit it in our platform with very standard fixtures. Here in this photo, you can see an image as well of 2 CubeSats that we launched last July in Castilla y León in Spain, where we have 3U CubeSats from 2 universities as well, that they were performing different missions. So for example, this satellite here to the right from a university called FUGHT as well, they were observing forest masses, so density of trees, in order to study how, for example, deforestation is affecting as well climate or as well the erosion of the soil and rivers. Because you know, trees perform a very important role in keeping the soil together and avoiding erosion. So that was the main target of this satellite. This other satellite from UPM, University of Madrid, as well, was designed to study the stratosphere itself. So it was taking measurements of the temperature, humidity, density, in order to improve the atmospheric models that are used, for example, worldwide, and improve those measurements. So, for example, we can have better predictions of, as an example, balloon trajectories or any other aircrafts or stratospheric aircraft, such as, for example, the Zephyr, flying in those conditions. So these are 2 good examples as well of flights that we can perform. So particularly this flight was up to 20 kilometers of altitude. We stayed flying around 2 hours in the cruise altitude before we send it down. So as I mentioned, this was a short mission example, but we can fly for longer time. Then as well, I wanted to share with you some other examples as well to give you ideas of the kind of solutions that we could easily do with the stratospheric balloons. So the first one, it is about, for example, demonstrating satellite constellations or satellite swarm flights. For example, now that satellites flying information and communicating within themselves are, let's say, a hot topic in the industry because they could perform a lot of activities, such as, for example, doing Earth observation activities using multiple instruments at the same time. So, for example, instead of having, let's say, a very complex instrument, for example, that works in different sides of the spectrum, you could have cheaper instruments, each of one working in a different area of the spectrum, taking information about a certain area, and then working together and sending that information to the command center. We could have better quality data sent back. So obviously these operations in terms of communicating with the other satellites are quite complex. And as well, there is always like a formation flight and the mission lead as well, and the other satellites that report to the lead. So you could demonstrate your technology by easily flying several balloons at the same time with different payloads, different satellites, and proving your whole concept of operations in a stratospheric flight. So instead of having to launch different satellites to different orbits to perform this exercise, you can have a much cheaper demonstration using our stratospheric balloons. So this is only an example of what can be achieved, but let's say the implications can be endless. Another one is as well another hot topic in the industry, which is satellite-based IoT. So you know that there are a lot of companies now that want to provide IoT services everywhere. So in remote areas where there are not, let's say, cell towers that are able to connect with the IoT devices with 5G technology. Now, a lot of companies are proposing the use of satellites to act as well as repeaters, as the cell towers, and then provide that communication service. So as well, if you want to test how your system behaves, because you have these kind of agricultural IoT devices, or you have IoT devices that are tracking, for example, ships, routes, you could easily as well fly a balloon or two within the interest area and see how it communicates with the IoT devices, how it sends information back to the control center, to the ground station, and be able to adjust all of the basically your operations. See how you communicate with the ground station, how you communicate with the IoT devices, study the latency of that communication, effectiveness, if you are able to cover a wide area or not. So this can be used, as I mentioned, for multiple applications. Agriculture, tracking of assets, can be done as well for surveillance. So many different applications that can be done and proposed using as well, demonstrated using our balloons. For example, other kind of applications is as well, for example, imagine that you want to deploy emergency communications. So in case of natural disasters, because I don't know, for example, now you may have seen that in Spain, in La Palma, there has been a volcano that has been erupting and has been creating a lot of chaos and a lot of damage to the local infrastructure. It's basically breaking communication lines, roads, etc. So imagine that had affected as well the communication network. So you could easily deploy a communications payload on a balloon and having it as well providing this communication link. This is probably more like a HAPS rather than near space testing, but if a company wants to develop a similar system, it can be tested as well first in our balloon flights. So now as well, I'm going to share a little bit more about the operating environment and the loads as well that are going to be suffering, just to give you an idea of how it's going to affect your payload and what data can you get out of it. So before that as well, showing you as well which stratospheric balloons are we using. So at the moment, we are using basically two kind of balloons. The first ones are zero pressure balloons, and we are developing our own super pressure balloons. Super pressure balloons as well, and hybrid balloons, will allow us to control the altitude at which our balloons are floating. So as well, that in the future will give us navigation capabilities to be able to keep a balloon stationary or around a certain area of interest for longer. So as well, this will benefit our near space testing service because we could keep our balloon in theory for months in the same location. So the length of the test that can be performed increases dramatically. But here what I wanted to show you, it is as well how the balloon sizes changes dramatically according to the altitude that you want to achieve and the mass that you want to achieve. So for example, here we have an example where if you want to take 100 kilograms to 25,000 meters, your balloon is going to be approximately 5,000 cubic meters big. But if you want to have the same payload as well at 35 kilometers, your balloon volume increases exponentially to 700,000 cubic meters. This is because the atmosphere as well thickness density drops as well exponentially, making it more difficult to climb higher. So that's why the balloon altitude limits, it is usually around 40,000 meters, 40 kilometers, and it is mainly because if not, we'll have to be building bigger and bigger diameters of balloons. So just to give you an example, the balloon that we are going to be using for our Raccoon system, how we are going to be launching satellites into space with a rocket, is going to be 110 meters tall. So bigger than the Big Ben in London. So just to give you an idea of how big this will be. Here is more data as well about the stratosphere and how the payloads that we're flying have to resist extreme conditions. So in terms of temperatures, there is quite a big drop of the air temperature as we climb to the troposphere. But then when we reach the stratosphere as well, slowly starts as well to increase again. So, but as well, I want as well to remind you that I mentioned before that the air is very thin, has very little density, so there is very little convection at these heights, at 30, 35 kilometers altitude. This means that areas of your satellite or payload that are exposed to the sun will get extremely hot because it will be more difficult for them to radiate heat out or to remove heat with convection, which is negligible. But colder, basically parts on the shadow will get extremely cold. So they will get to this minus 40 or minus 50 degrees. So as well, that is why it is interesting for testing, because are conditions that are similar to the ones that we will face in orbit. In orbit, temperatures will be higher as well in terms of higher temperatures, but and as well then lower peaks. But as a first way to test, it is very interesting. And you can see as well the pressure drops dramatically with altitude. This means as well that at this altitude, we can start as well seeing the effects that vacuum can have on materials, or as well on propellant containers. If you are designing a small propellant container for a CubeSat to provide, for example, altitude control, you can test it in these near vacuum conditions to see if it will resist those loads. You know, your tank will be pressurized at a certain pressure, outside there will be zero, so that creates a big stress load on the container itself. So, and here to the right, there are some as well real life measurements as well taken in different flights that we have performed. So here's how the pressure drops quite linearly. And here you can see how the temperature changes. Well, just to let you know why it has this shape, it is quite funny because we started the flight quite early in the morning. So we had lower temperatures, but then when the sun started to hit the atmosphere, that was when we were coming back, we had higher temperatures. So that's the main reason why you see this and not, let's say, a straight line like we have in here, because the sun heat is the air, and therefore provides these other conditions. But anyway, it's as well a good image to show you how temperature decreases up to the tropopause and then it starts to increase when we keep climbing up. Then about solar flux or radiation. So as well, there is something very interesting as well on the stratosphere, which is as well that due to the magnetic field of the Earth and the ozone layer, the stratosphere is an area where a lot of solar particles and cosmic rays, let's say, interfere with the ozone layer. So the density flux of these elements, it is quite high. This changes depending on the region, so on the latitude. So when we are closer to the North Pole, where most of these particles enter the Earth because of the magnetic field of the Earth, it increases. In other closer to the equator, those fluxes are less important as well. But something very interesting, it is as well that linked to what I have just said before. Here you can see, for example, how basically the cosmic radiation of different particles, protons, neutrons, electrons, actually peaks around the stratosphere, which is where we are flying, and decreases later on as well. This is as well because, as what I mentioned, the magnetic field action on the Earth. So that means that in the stratosphere, sometimes we have higher radiation levels in terms of cosmic rays than, for example, in low Earth orbit at 200 kilometers, which is an interesting finding as well. So as well, here there are more figures as well to illustrate the energy of those particles, that it provides a very good example of why as well the stratosphere is a very nice place to test against radiation. And then as well, this is a little more information about the neutron radiation. As I said as well, depending on the latitude and the altitude, and then on the latitude, this information will change. So as well, here's some more details of how it changes with altitude, and then with the latitude as well, how as well it is increasing. So in the equator, it is lower, and we were close to the poles, the North Pole, it is as well increasing. So, well, I think this is it at the moment. This is the end of the presentation. So I hope you enjoy it. And now I'm happy as well to answer any questions, comments, or doubts as well that you want to share. So as I mentioned, any questions, please write them into the chat, and I will be answering them. Or if you want to speak, raise your hand, and we will ask as well to unmute you, so you could raise it as well too. So don't be shy, please, and ask as many questions as you want, or any curiosities or any comments that you want to ask. So how much, there's a question from Steven, how much control do we have over the flight path? Well, this is a very good question. So the good thing is that we have very powerful tools that we have developed internally that allow us to predict and control the trajectory. So it is taking predictions from from weather satellites that give us information about the different wind speeds at different layers of the atmosphere. That means that we will know, for example, the latitude speed, how, for example, it's drifting east or west, so north or south, and the longitude as well. So as well, based on that information on each layer of the atmosphere, we are able to accurately predict where the balloon is going to be flying. Therefore, we can plan the mission. Or as well, we can do reverse engineering. That means that we want to fly in a certain area. So with these tools that we have developed internally, are able to find out from where we should be able to launch it. So we are over that area of interest. Okay. There is another question from Toshisha. Yes, could you share the planned future schedule for near space test in 2022? Yes, we will provide as well that information as well on our website soon. Just as well to give you an idea, we have already planned flights for next year on this near space testing service. The first flight is expected for March 2022. We still have slots available as well to book in case you want to fly your payload. And then the next flights will be in June, July, and August. Good. Then as well, we have another question from Michael. How is recovery of the system control unaffected? Example, landing and splashdown. As well, very good question. So as you may have seen on our presentation, we have the stratospheric balloon. Then we have a flight train, which are the cords and parachute as well that go down to then our test bed, which is the gondola or the structure that holds the experiments. Once the mission has finished, we activate a set of pyrotechnics, pyrocutters, that cut the payload loose from the balloon. That means that we separate the balloon from the gondola, and then the parachute opens and everything goes down slowly on a parachute. As you could see as well on our presentation, our structure, our near space test bench, has some actuators as well that soften the landing. At the moment, we are working to land most of the times, or as let's say, always to land on the ground, which is as well interesting because in that way we don't have to provide, let's say, water protection, because you know that obviously if your electronics component get, I don't know, water in ingress, for example, or seawater, they're going to be ruined. So that's why we try to always fly in above the ground. Then we have another question from Julio. what level of maturity you can get for equipment or systems with this near space testing. So, well, basically, according to ESA, there are different, or NASA as well, there are different levels of TRL as well levels. For us, we can basically, what we as well can provide is that it is at least a TRL 7, so demonstration on a relevant environment, or TRL 8. So depending on the application that you want to demonstrate, this can increase your maturity level, or you can demonstrate your maturity level as well to to a certain degree. It is not going to be, let's say, TRL 9 in terms of space flight proven, because obviously it has not been in space, but can get you very close to basically have fulfilled the other previous validations and then just perform the final test. Okay, then we have another question from Eladio. Can you close the radiation seen by the payload? Yes, for example, what we can do as well, for example, if your payload has a specific requirements, we can provide insulation to your payload. So if you want that your payload it is not suffering anything, we can provide a physical as well protection for this. So basically, we will enclose it in a small box, and as well try to, depending on how sensitive to radiation is your payload, we could work together in proposing specific insulation method. As well, we are talking with the other companies, for example, that to integrate active radiation prevention methods, basically having like a small magnetic fields around to develop, basically divert the particles. So we can, let's say, try to attempt that either by physical means, basic insulation, or active means, but that's something that we are still working on. Good, then we have another, sorry, sorry, I've said as well that if we can measure the radiation, that was the comment from Eladio as well. I mean, depending on the mission, we can as well take on board with us radiation sensors. So, for example, that's something that we have already done, flight radiation sensors. So we are able to measure the level of radiation that your payload has received and try to compare it with what you have already measured, or what if you have onboard equipment to compare the data. So yes, we can onboard radiation sensors in order to measure the radiation that your payload has received. So we have many different potential applications, such as, for example, we can provide you all of the information about temperatures, pressure, density, radiation levels, temperature, not only, let's say, outside, but as well we can measure temperatures of your payload itself. So the kind of service that we can provide, it is quite wide. Okay, then we have another question from Robert. What lifting gas are you planning on using for the full-scale balloon? So that's a good question, because as I don't know if you're aware, but helium gas is a finite resource as well, and it is getting very expensive. So helium as well is usually a byproduct that it is obtained from natural gas deposits, and as well as all of, let's say, petroleum derivatives as well, or things that are linked to these kind of exploitations, it is a finite resource. So now there have been discovered some reserves in Tanzania. There are some reserves as well in the US, but it is becoming a scarce resource and more expensive. The price has more than doubled in the last 3 years. So as well linked to this, we are planning as well on changing from helium to hydrogen, and as well studying forms of which we can use hydrogen obtained through renewable energies and sources. So, for example, here in Wales, there is a company that it is planning to produce hydrogen from waste plastic. So we are already starting conversations to see how we can help, for example, in this kind of circular economy, and use these kind of sources to use hydrogen. Obviously, hydrogen has challenges. Everyone, when we talk about hydrogen, remembers the Hindenburg. So obviously, that's something that we have to take care of, and obviously, some kind of safety precautions, such as avoiding electric discharges, static electricity that can create a flame to combust. It is something that we are going to take into consideration. But as well, to let you know, it is not that easy to, let's say, to burn hydrogen. You have to have a right mix between hydrogen and air in order to be able to then achieve combustion. But anyway, it's something that before implementing any solution with hydrogen, we will have basically spot on a solution and have it work out good. Thank you. Then we have another question from Matthew. Hi, Valentin. With your exciting balloon product, how does B2Space look to keep up with demand from your clients, and will you be looking to expand the business? If so, how will you go about doing this? So, well, at the moment, we are going to be keeping up with demand by doing more and more balloon flights. So this year we have already performed 4 balloon flights, let's say our zero pressure balloon flights. Next year we are going to perform more of them. So what we are going to be doing is increase our rate of flights. As I mentioned, for next year we already have dates in March, June, July, and August. June, July, and August, as are the, let's say, in the northern hemisphere, the areas with, let's say, or the months with better weather, we will perform 2 flights each month. So let's say that we have already 7 flights scheduled for next year. If demand keeps growing, we will be putting more flights. And then if, for example, we, let's say, start feeling a lack of good launch opportunities or window weather opportunities to launch here in our current launch locations, what we will do as well, as I mentioned, working in another launch location so we can maximize the flight opportunities that we can offer to our customers. So for that as well is why we are opening, we have opened, for example, the subsidiary as well in Spain, but we are as well looking for other locations too. Then another question from John Holmes. What is the transit time from launch to altitude? Usually, as well, it depends on the conditions that we want to achieve. Our ascension speed, normally it is between 1.5 to 4.5 meters per second, and we will define the ascension speed on different factors. First, on the planned on the flight plan, so where the winds are going to take us, and if we need to go to the, let's say, to the cruise altitude higher or slower. Going higher means that, yeah, that we can get earlier into, let's say, cruise altitude. But then as well has some challenges, such as the gas is going to expand more quickly, and as well it's going to be, let's say, a more of a bumpy flight. If we go slowly, let's say the balloon and the payload will be, let's say, in a more relaxed flight, but as well it will take longer. But on average, it's something between 40 to 90 minutes, depending as well on the, as I mentioned, on the ascension speed that we select. It is something as well that can be customized, both the ascension speed, but as well the altitude that we can get to. Good. There are no more questions. Don't be shy. Any questions, curiosities, funny facts? Feel free to share them. Okay, another one from Steven. I know that NASA launched from Antarctica. Would you consider launching from the poles? Well, I mean, that's something very interesting because in Antarctica, well, there are 2 main advantages. One is that basically there is no population around. So if your balloon goes down, there is, let's say, no safety issues. So let's say you can fly very big payloads. And then as well, due to the local weather conditions, you can keep the balloon flying for a long time on the area. And that means as well that you can perform experiments for a long time. So that's, for example, why NASA has launched in the past stratospheric balloons with telescopes on board on Antarctica in order to study different things. So for us, to be honest, it is something that it's a dream. I would like to, well, personally, I would like to go to Antarctica and launch our balloons there for different missions, even, I don't know, study the ice sheet, or as well launch on behalf of NASA some of their space telescopes, or for ESA. I will not discriminate against each other. But yeah, for me, it would be, I mean, a dream to go there. It has some challenges as well because it's a pristine environment. So we need to make sure as well that we don't contaminate it. But yes, it's definitely something that we would consider. Okay, now we have a question from John. It is planned to operate in several countries. How do you find the challenge of dealing with multiple regulators, and does this limit your options for switching sites even within a country? So within a country, it is not a big challenge. So for example, in Europe, we are following the CAA regulations or EASA regulations that are similar in all Europe. So as long as we meet certain criteria, and we engage with the air regulatory bodies, it is not a problem. So it is the same for each country. Obviously, we cannot fly, let's say, for example, from London, because it's a heavily populated area. So if something goes wrong, there is more risk of of hurting property or people. But within the same country, it is not a problem. In terms of operating within different countries, so as well as I mentioned, EASA for the European Union and for Europe has a clear set of regulations that are the same. What changes is mainly, for example, the Ofcom, or let's say radio frequency operations. So we will have to ask permissions to use different kind of frequencies if it's required, because we want to transmit, for example, in UHF, S-band to test different technologies. So we will have to get in each country permissions to use those frequencies. For example, if we are as well splashing down on the water, we may be requiring to as well ask for the maritime authorities to have this permission to land on the water and then recover the payload. So that will change from country to country. But in most cases, when we are testing standard components such as radiation sensors, avionic units from CubeSats, full CubeSats, it is not a big problem, because there are quite standard regulations that we can that we are already used to, and it is quite agile. So that's why as well we already are starting to launch from different countries, because we already understand the regulations, the rules, what has to be done, and can do it quite quickly. Okay, it is feasible, and do you have any plans to implement any kind of propulsion or maneuvering on the system? Yes. Well, the question is propulsion, probably not, because the main thing is that, as you can imagine, the balloon is a very large object. So it will be moving with the atmosphere, with the air at the same speed, and it has such a large surface that moving that with, let's say, a propeller or any kind of other system would require a lot of energy. So how we are going to obtain propulsion or maneuvering capabilities, it is by developing hybrid balloons, something similar to what Google Loon already achieved, which is we are changing the density of our balloon, and by that we are changing the altitude at which the balloon is floating. In that way, we want to benefit from the different directions of the wind at different layers of the atmosphere. So for example, if we keep the balloon flying at 23 kilometers traveling west, and then we make it go down because we change the density by pumping air in and make it, I don't know, go up 14 kilometers of altitude where the wind may be going to southeast. By performing multiple changes, we can keep the balloon within a certain area. This is something that Google Loon has already demonstrated, and although they have shut down, let's say, the company for their communications purpose, they have released all of the documentation and information on how they achieved that. So that link to our own developments will provide us the capability of maneuvering and station keeping as well, hopefully very shortly. In our plans is by the end of 2022 or early 2023. This is not going to be possible worldwide because of, for example, in the northern latitudes and as well very southern latitudes, the winds are quite constant, always in the same direction. So this is only achieved most likely within the tropics, where we can have this kind of altitude changes to keep the balloon within a certain area. But that's the way how we're going to achieve this kind of maneuvering and station keeping capabilities, therefore increasing by months the time that we can spend testing components. You're welcome. To be honest, stratospheric balloons, it is quite, I mean, it looks quite simple, like sending a balloon up, but has a lot of challenges. But then as well, the possibilities it opens are so interesting that it is, I mean, quite a challenge, but something that we enjoy a lot. Okay, another question from Matthew: does B2Space just launch from Europe, or as demand grows, will you need to look outside at Europe, or for site, do you feel that you can meet demand solely from Europe? The regulation you kindly mentioned you will need to adhere to. Okay, just I had a very interesting conversation a few years ago with a number of European companies who are looking to keep European business in Europe and reduce reliance of US-based launch site. Yes, I mean, we will perform in Europe, obviously, let's say, because we are based here in Europe, as many launches as possible. But as we grow, if required, for example, or to perform longer testing until we achieve our station keeping capabilities, or even after that, we will be testing from different parts of the world. So that's, for example, why we have already engaged with Australia to perform stratospheric flights from there too. That means that, for example, in Europe, we will be able to serve the local European market. And from Australia, for example, we could absorb the excess capacity or the excess of demand that we have, and then as well absorb work, let's say, from Asia, Pacific region, Australia, New Zealand, Indonesia. So that's our strategy. In terms as well of potentially launching from the US, in the US, there is, let's say, already a large company performing activities, not like us, but let's say similar. A company called Raven Aerostar that is expert on stratospheric ballooning. So potentially for us, it's not, let's say, so interesting to go there and because they are already established there and it's going to be more difficult. And second, because they have more restrictions in terms of ITAR things. So I mean, we are not close to that opportunity, obviously, and we would love as well to work in the US and with US companies. But it is true that there are some more regulations and that we will need to take a look to that carefully. We are at the moment used to what it is done in Europe and as well starting to get used to what it is done in Australia, but we'll have to take a look as well to other potential things. But yeah, we would like to keep as much as possible, let's say, within our in areas where we are not reliant on any third parties. Do you see a limit? Another question from Steven. Do you see a limit on maximum payload volume for balloon flights? Well, not really. We could as well, in theory, potentially design as well as specific fittings to hold any kind of volume. So, well, for example, we are working with a large Spanish company on a proof of concept as well of some of their technologies. And we're talking about building a gondola, a structure to hold their payload that will be approximately 2 meters wide and 2 meters deep. So we can potentially design solutions to basically hold any kind of payload. Let's say the most restrictive element will be weight. At the moment, the largest balloons that have been ever built have been able to lift up to 4 tons. So this is probably the limit of what we will be able to achieve in the future. Larger balloons than that, let's say, to be able to carry 10 tons, 15 tons, are feasible. However, they would be so big that would require a huge investment just to manufacture them, to have the, let's say, the right infrastructure and machines and methods to manufacture it, inspect it, and as well check that it is right. And then obviously they would require a lot of filling gas. With hydrogen, it shouldn't be an issue, but at the moment it's something that we don't think there is a, let's say, a market over there to go that high. So that's why we are keeping it at the moment to 100 kilos, and we will be growing it mainly for our Raccoon solution, but not in principle for near space testing. Although if, I don't know, tomorrow or next week, ESA comes to us and says, okay, I would like you to test a descent module that ESA is preparing for Mars and how the parachutes will open and how everything works, for sure we will work on them. We will work on that project with them. And that's, for example, one of our main aims as well, to become here in Europe the reference for these kind of activities. You're welcome. Any other questions? Any other comments? Don't be shy. Thank you, Esther, for that, for your congratulations. Good. Thank you as well, Michael. I'm glad that you enjoyed the presentation. Well, if there are no more questions as well, what I would like to say is that I have enjoyed this presentation a lot. I hope that you have enjoyed it too. This is going to be uploaded into our website as well, so you will be able to see it, to share it with anyone as well that you think can be interested. If you want to know more, please get in touch with us, either through our website or add us in LinkedIn, and we will be able as well. I'm happy to discuss with you further details. As I mentioned, we can do any kind of test, so we can perform specific missions, design experiments, anything that you think of, we can do it most likely. Not as 100%, but most likely we will be able to perform almost anything that you propose us. So please feel free to reach us. And again, thank you for your time and have a good afternoon.